Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm the interim director of NITheCS. And today I'm very happy that we have another talk on quantitative finance, because since this year we have also a very famous research program on quantitative finance. And I will invite now Dr. Mesias Alfeos to introduce our today's speaker. Mesias.
Thank you very much, Francesco, for the opportunity to introduce the speaker for today. Today, it's a great pleasure to welcome Professor Erik Schlögl from the University of Technology, Sydney. He is a full professor in the School of Mathematics and Physical Sciences. He is an expert in quantitative finance, and I'm really grateful for him to be here physically, especially in particular that he was my PhD supervisor, and all the knowledge that I have tapped from him. And Professor Erik is an expert. He published a lot in quantitative prestigious journals in quantitative finance, and he served an expert in most of the quantitative court case in Australia, and he also invited at major conferences as panel speakers, and he organized many major conferences in Sydney in quantitative finance. Erik, today we are really grateful. We're honored to have you as a speaker at our colloquium, and he is going to talk to us about the SOFR, which is a secured overnight financial rate, term structure dynamics, and a discontinuous short rate, and stochastic volatility forward rate. We're very honored to have you again, and you have 1 hour to give us the talk, and we're looking forward to talk to you. Please, people, the audience online, as well as the one in the room, please help me to welcome Professor Erik Schlögl.
Thank you. I think I'm on speaker here. So, well, thank you very much. And first of all, thank you to Messias for inviting me here. It's only my second time here in Stellenbosch, and the first time actually giving a talk in person. Messias had me give a talk virtually during the pandemic. So, but this is of course much nicer and in such a nice setting. So thank you very much, Messias, and also to NITheCS for having me here for this talk. So this topic here, this is actually joint work with two people. The first one is Carl Gellert, who is my PhD student, but he's also already a very experienced interest rate quant, and he was actually working as an interest rate quant for the Bank of America for most of the time that we did this work. He's now changed jobs, but I'm saying this because also Alan Brace, of course, who's well known in the interest rate term structure modeling community, he used to be at National Australia Bank, so also somebody who is not based in academia. So this talk certainly, under the influence of my two co-authors, has hopefully a very practical flavor to it, though of course this is quantitative finance, so there will be equations, there will be mathematics in it. So I want to talk about SOFR term structure dynamics. So SOFR stands for Secured Overnight Funding Rate, and it's one of the new interest rate benchmarks that is, or actually already in some jurisdictions has replaced the old benchmark, which was LIBOR, right? So it used to be that the London Interbank Offer Rate, LIBOR, was the main interest rate benchmark worldwide, either LIBOR itself, so traded in London, or various versions of it. And I do believe that there was a version of that in Rand here in South Africa as well, and perhaps still is. It's just that things have changed. And some jurisdictions are moving away from this, not all. So there's a Euribor, which is the euro version of it, which may not disappear. But certainly in the US, they've changed SOFR, and also the UK, they're changing to their own version of this. Okay, let's get this clicker to work. Or maybe not. I'm having some trouble here. Advancing my slides. I'm sorry. Ah, no, that's better. Now it works. Okay, sorry about that. Right. So, what are we on about here? Well, historically, interest rate term structure modeling has been based on these rates like LIBOR, which have a substantially longer time to maturity than overnight. So typically something like 3 months. That's a very typical time to maturity for these benchmarks. And these and that of course then flowed on to the mathematical models for the term structure of interest rates. And that means that it was modeled either directly, like in the well-known LIBOR market model, or indirectly, meaning that even when you had rates where the basic mathematical object that was modeled was a continuously compounded short rate, so something like an overnight rate. Oops, we lost the screen. Didn't do anything. Should I just wait for that to come back? Right. Okay. But anyway, I mean, this slide, at the moment, I'm just on that first slide, so I guess I can just keep talking until it comes back on. So what I was saying is that even in cases where the basic object of the mathematical modeling was something closer to these very short-term maturities, nevertheless, those models were typically calibrated to the market based on longer maturities. So historically, any regard to the actual overnight rates, which form the basis of these new benchmarks, has at best been an afterthought. But now with benchmarks like SOFR, this has changed, right? The overnight rate, that becomes the primary market observable. So the thing that you can calibrate your model to, or that you can estimate your models on, and term rates, like 3-month rates, they actually become a lot less readily available and must be inferred, for example, from derivative contracts like futures. So that means then that the idiosyncrasies that these overnight rates have, they can no longer be ignored as they used to be. And more than longer term rates, these idiosyncrasies for the short term rates are driven by monetary and regulatory policy, right? So rather than prices forming in the market, these rates are driven by whatever the central bank decides. So in particular, this means that the model must reflect jumps with deterministic jump times. And the mathematical literature typically refers to these as stochastic discontinuities. So those are stochastic processes which have jumps, but not like a Poisson process where the jump occurs at some stopping time. No, the time of the jump is known, just the size is unknown. And of course, the idea behind that is that, well, we know ahead of time when the central bank rate setting committee meets, so we know when there's going to be change in the rate. And the other thing that's changed quite substantially since the time when originally these interest rate models were developed is the amount of volatility that's actually in these overnight rates, right? So what we've got here is a graph of the changes in the effective Fed funds rate. So that's one example of such an overnight rate. And as we look at that, and we've got there marked on that graph over the timeline, the time when various famous models in interest rate term structure modeling appeared. So there's the model by Merton back in the 1970s, then Vazicek, Coxinger-Soros, Howe-White. So those were all quite well-known models and which were used quite extensively also in the markets. And you can see that when those were used, there was one could say that there was quite a bit of volatility in this short rate. So perhaps a diffusion-based dynamic would have been a good approximation. But then we had the financial crisis, right, of 2007, 2008. And one result of that is that the central banks really flooded the markets with liquidity, with money. And that really reduced the volatility in the short rate, initially to almost nothing. It then came back a bit. Now it's actually come back a little bit more, but still nowhere near what it used to be. So That means that's another reason why these old models are not necessarily a good reflection of reality anymore. So here's another thing that we can look at. So again, we've got our short rate. So that's so the black line is an actual market rate, and we've got the red line, which is the decision rate, so the target rate set by the central bank. So in this case, again, U.S. data. And what we see there is that at least the first order, well, certainly the target rate follows like a step function, and the market rate, so it's the rate that actually is traded at in the market, that follows a very quite similar dynamic. And again, to first order, perhaps it's a step function. Historically, there were these spikes, as you can see there in sort of the early phase here of that was mainly due to end of month effects where the banks had to cover particular positions due to regulatory requirements, right? So it was an artifact, but the regulators wised up to that and got rid of those requirements. So these days, those spikes that we see, that don't really happen anymore, so we don't have to worry about them. We also had in September 2019, there was a major spike in the market, right? So this was all due to basically the market starting to learn to deal with these rates. But nowadays, it's much more like a step function, right? So you can see that here at the end. There is still a little bit of discrepancy, but not much. So if we certainly to first order, we want to capture this if we ever want to construct a model for this market. On the other hand, if we look at forward rates, right, so forward rates are interest rates that we agree on now, either borrow or lend, starting at some date in the future. But we agree on that right now. And so those things that look a lot more like diffusion processes there, when the three different colors, those are the forward rates implied by three different contracts traded in the market, each for a 30-day maturity. And you can see that they actually still look rather diffusive. So we actually have a conundrum here, right? So we need to construct a model that reconciles these two things. Here again, we have another example of this. So this is actually, before I was showing you EFFR, the effective Fed fund rate. That's not the benchmark. You might say, well, SOFR is a benchmark. And again, we see exactly the same effect. And we also see this effect of some major spikes. So there's again that big spike in September 2019. But that has in recent years disappeared. Right? So this is really the most recent history. So again, to first order, we have these stochastic discontinuities. We have these jumps at deterministic times, and then perhaps overlaid by a little bit of diffusive volatility as well. Right, so EFFR and SOFR both appear to follow similar, largely stepwise paths. The spikes have sort of disappeared, and those are the features that we need to model. Right, so again, this slide just repeats what I've said, so I'll just go through this relatively quickly. So what we're seeking to do is to reconcile these stepwise, mostly constant and jumping at known times dynamics of the short rate with the diffusive dynamics of the forward rate. And one could interpret this as follows, is that the forward rates that we actually deduce from these Fed fund futures, that they reflect the expectations of future interest rate changes, right? So the short rate, that's determined by what the central bank says. The forward rates, they depend on what the market expects the central bank to do. And of course, that changes from day to day as new information arrives, right? So that remains quite diffusive. Right, so here's the basic model that we started out with. So this is what we call a Gaussian forward rate model with piecewise volatility. So it's Gaussian because everything, all these coefficients here, they are deterministic functions of their arguments, so deterministic functions of time. And this is and these are Wiener processes. So obviously, this is going to have these Fs, they're going to have a normal distribution. So that's why it's a Gaussian model. And the reason why we call this piecewise volatility is because this volatility function that we have here in the stochastic integral, that switches on and off only if there's still a meeting date at some time in the future. So this f little t big T, that's a forward rate. That's a rate that we contract at time little t now for a future borrowing or lending at some big T in the future. And if there is no central bank meeting date in between now and that date in the future, then nothing can really happen to our rates. So there's no volatility. If there are meeting dates, then for each meeting dates, we have some volatility in the changing expectations of the market of what the central bank is going to decide on that meeting day. Right? So that's what this expresses here. So there's some constant volatility for each component times these indicator functions, which ensure that the volatility is turned off when there are no meeting dates. So we can then just rewrite this or solve this stochastic integral, because that's relatively trivial in this case, and rewrite it like this. And so each stochastic component then corresponds to a central bank meeting date. And then any changes that the central bank decides on that date, they're then carried forward in our target rate from then onwards. And it's the indicator function that ensures that the ith factor only applies to the ith meeting date, which means that if there's no meeting date coming up between now and the maturity of some rate, there's nothing happening. So there's no diffusion component. Now, this then ensures that our short rate, right? So taking the forward rate, but setting the maturity date, so the second argument, to now, then it becomes the instantaneous rate right now, right? Before, that was a big T for contracting for borrowing or lending at some future date. But if we set that to now, then it's the rate that's valid right now. That's the so-called short rate. And if we then plug that into the equations that we've set up, we see that this short rate will have exactly the behavior that we want, right? It'll have no diffusion up until the next meeting date, at which point it picks up everything that's happened in between. So it jumps, but by a random amount based on what's happened in the background with the diffusion up until that point in time. Now, once we've set that up, the convenient thing about the setup that I've just given you is that the factors are directly identified with the central bank meeting dates. But of course, then it would, if in that case, it's unreasonable to assume that the factors are independent, right? So what the central bank decides at the next meeting, that will influence what it'll decide at the meeting after that. Right? So we can't just say that two are independent. However, for mathematical purposes, it's actually convenient to reparameterize. So basically to rotate our driving Wiener processes in such a way that the factors are independent. Right? So we can just do that as I explained here on this slide. And then the advantage of that is that then we're immediately in what's known in interest rate term structure modeling as the Heath-Jarrett-Morton framework. So we can use well-known results to rewrite, first of all, the dynamics of these forward rates under what is called the risk-neutral measure. Right? So, well, there's a whole course that NITheCS teaches that actually explains what risk-neutral measure actually means. In short, it's the probability. It's a probability measure that's equivalent in a probability theory sense to the true probability measure under which things actually happen. But it's such that we can use that probability measure to directly calculate prices as expectations. And that sort of equivalent probability measure has to exist, because otherwise one can make infinite profit at zero risk. And that cannot happen, right? So therefore, there must be such a risk neutral measure, and we can then therefore work directly under it, because it's just convenient to do that when we want to price financial instruments. Right, so that then allows us to rewrite this directly under this measure, which we can then use to price derivative financial instruments. We need to be able to do that in order to then calibrate the model to the prices that we actually observe in the market. Now, one interesting thing that one sees from this is that if we then take the result from the previous slide and write down the short rates, so again setting the maturities, so the second argument of our F to now to little t, we get this result. And it shows us, first of all, well, it has these Gaussian dynamics, stochastic term, but that's how we set it up. But on the other hand, it also has to have this particular deterministic term. And that particular form is, in this model, the only form that is consistent with the absence of arbitrage, right? Consistent with the assumption that we cannot make infinite profit at zero risk. And the reason why this is important is because it tells us, well, we cannot arbitrarily interpolate the term structure of interest rates. Right? So a term structure of interest rates is just a function that gives us interest rates for all possible maturities between now and some time horizon. But the market, of course, doesn't give us the whole continuum. It only gives us points on that term structure. So anything in between, normally we interpolate, and in practice, normally one does that relatively arbitrarily. But in this model, one cannot do that, right? There's just a specific form that this actually has to take. And that's given by this equation here. Right. So once we have those results, we can then proceed to price instruments that we actually observe in the market. So in particular, futures contracts on both the Fed funds rate, so this EFFR that I had there before, or on the new benchmark SOFR. So here we're looking at 1 month futures contracts, meaning those are contracts where, well, we contract today for a payoff at some date in the future. That's why it's called a futures. That is based on the accumulated interest over a particular period, in this case, 1 month. And you can see how that accumulates there because we're summing over these interest rates. Okay, so this accumulation here for the 1 month futures happens to be done by just summing the overnight rates together, which is actually very convenient because when, as I told you before, we can price these instruments under this risk neutral probability measure just by taking expectations. And so we can write the futures price as this expectation here at the bottom of the slide. And because that thing up there is so nicely linear, we can, of course, write that as a sum of individual expectations, which makes things a lot easier, which and then we can immediately calculate, right? If you think back at the equations we had for R before, that's relatively trivial because it involves a deterministic term plus a stochastic integral. The stochastic integral has expectation 0, so away we go, right? Yeah? Yeah, well, that's considered to be fixed, right? So that, or implicit in a way, right? Yes, it does. It does depend on it, but that NM, of course, is fixed and it doesn't evolve. So the NM depends on the M. So if we're just so just a short notation, we can just make everything depend on M. Okay, so using those results, we can then proceed to calibrate the model, meaning we want to choose the parameters of the model so that at least at one particular point in time, the prices that we get out of the model match the prices that we actually observe in the market. That's what's meant by calibration. And for that, we use the first 12 monthly Fed funds futures contracts. We assume a piecewise flat initial term structure. The drift impact, so that was the story that I was telling you about here about the deterministic term, that we actually ignore that because numerically it's negligible. Okay. Theoretically, one needs to include it, but practically it doesn't matter. Also, we have no spikes in the model, right? Because they've disappeared recent times. We assume that the spread between the target rate and EFFR, so the difference between the two, is just constant, which to first order seems to be true, right? But obviously, this model could be extended by making that stochastic in some way. And we then define the calibration error as the not quite the difference between the model price and the market price. So we have the one FM and an FM tilde, right? So the FM tilde is what the model tells us the price should be. The FM is what the market says that the price actually is. So clearly the difference between the two, strictly speaking, is the error. But in the market, there is a limit to the numerical accuracy to which prices are quoted, right? They don't go on and on and on, right? In terms of many, many decimal places, they only go to a certain monetary amount called a tick, and that is given by this H0 and the HM. So we're basically saying that as long as we're within that, then we perfectly fitted the price. That's what that's saying. So just to test this out, we then performed the calibration on daily data from January 2015 to September 2020. And then once we calibrated the model, we looked at how well these future prices actually predict what the central bank is going to do, right? Because remember, earlier I said, well, these forward rates, and therefore also these futures contracts, they incorporate the market's expectation about future decisions by the central bank. And so we then actually just calculated the R squared between what these prices predict the central bank is going to do and what the central bank then actually did for different distances to the actual meeting date, right? So that days to jump is how far away, how far out we are from when the central bank makes its decision, and then we calculate the R squared. And unsurprisingly, right, as we go further out, as we have longer to go till that particular meeting date, the R squared drops off, but it doesn't actually go quite to zero. And if there are relatively few dates, little time until the next jump, the market actually predicts what the central bank is going to do relatively well. And actually, that's not surprising because that's the central bank's intention. The central banks always try to signal to the market what they're going to do. It doesn't come as a total surprise and cause all kinds of chaos. But the thing here that this shows is that the model actually picks this up. Okay. So those are, well, was the most important result of the results that we got out of this calibration, right? So fitting to the market at only a day at a time. But of course, normally what you do is you actually work with time series data, right? You do a proper estimation of your model, right? To get some sort of coefficients for your stochastic process that then hopefully you cannot reject the hypothesis that the true dynamics are as your model says they are. However, with the model that I've presented you so far, we can't do that. Simply because we lack the time homogeneity of the model. Right? Everything changes all the time, so we don't have the kind of time homogeneity or even stationarity that we might want for a proper econometric estimation. So the model needs to be changed with regard to the meeting dates. So now we have, instead of the previous volatility function psi, that is now replaced by this one, where the indicator that switches on and off a factor now is not based on a particular meeting date, but rather just on the number of remaining meeting dates. And that's time homogeneous, right? Because as long as we have, let's say, a fixed time period left to go, then most of the time, to a reasonably close approximation, we've got exactly a particular number of meeting dates that are going to happen in that time period, just because these meetings of the central bank or of the rate setting committee, they happen on a regular basis. Right, so that's counted by this script A. So other than that, nothing changes. Right? So all I'm doing is replacing that volatility function that I had before by this new one, so that we can actually do some econometric estimation. But we now want to do this on an even bigger data set. So on top of the 1 month futures, we also want to use the 3-month futures. And they're a bit more complicated. Right? So the 1 month futures, they just added up, they just added up the rates over the 1 month to get the payoff on the futures. These here accumulate the rates in a multiplicative fashion. Right? You can see there's a lot more complicated, which also means that if we wanted to work out the expectation of this thing within the model to get the model price, if we wanted to do that strictly correctly, we would have to resolve even in the simple model, we would have to go to numerical methods, and that would be a bit of a pain. So instead, we do this, right? So we take the equation from the previous slide, take the expectation on both sides, and then approximate that expectation by this expression. So by pulling the expectation inside, so doing all kinds of nasty violations of mathematical identities, right? So Jensen's inequality is violated, all that sort of stuff. But we then turned around and tested, does that really matter? And it doesn't, right? So this approximation is very accurate. We verified by Monte Carlo that we're actually allowed to do this without losing too much accuracy. And in particular, even if we do get an error, that error is stable over time. And because econometric estimation goes on, is based on changes, well, if the error is stable, then it's not going to impact the differences, right, between from one day to another. So it doesn't affect our econometric estimation. Right. So we then assume, but that's actually consistent with our model, that the forward rates are piecewise constant between the meeting dates, and we find the forward rates, and therefore then the model parameters, such that, so as to minimize this particular objective function. So basically minimizing the sum of the squared errors between the prices for the futures that our model gives us and the prices for the futures that we actually observe in the market. And we do this not just for the 1 month futures, so those are the F1s, but also for the 3-month futures as well. And then using principal component analysis on these calibrated states, we can then estimate our volatility functions, and that gives us basically these coefficients that enter into our assumed volatility functions psi, right? And I've called them gamma here because this is now split apart, right, into a volatility level component, which is sigma j, which is not factor dependent, and a factor dependent component, gamma ij. It's just a convenient decomposition of our volatility coefficients. Okay, so obviously, I mean, I don't expect you to necessarily have got your head around all the details of this estimation, how it worked, but that's not really the point here. At the end of the talk, I've got references to a paper where you can look that up if you like. I mean, our paper, I mean. And what we did, however, I want to talk about the results. So some other authors, Jacob Skoff and David Skoffman, in 2021, they published a paper of analyzing, so doing an empirical analysis on exactly the same SOFR futures that I'm going on about here. However, they used a model with just purely diffusive dynamics. So they use an old style model. And so it makes sense then, if I'm saying that our model is better suited to these new realities, is to simply do an estimation that replicates theirs, but using our model. Right. So what we've got here on this in this table, we've got four rows. The bottom row is the result that Skov and Skofman got in terms of their root mean square error, so how well they fitted the market. And the top three are our model, but for different numbers of factors, right? So, and the three factor is actually corresponds to the number of factors that Skov and Skofman used. So really, you should only be comparing the last two rows. And what we see there is that the root mean squared error for our model is substantially better. Right? So even though we're using the same number of factors. And this effect is particularly strong when we have relatively short times to maturity and relatively short terms for our futures. Remember, we were using 1 month futures and 3 month futures. Now, if you compare and 3 month is quarterly, right? So those are the Q columns there. And you see that there's not much difference between us and Skov and Skofman, right? So it bounces around a bit, actually, more or less the same. And for the 1 month futures, which those are the M's, we get substantially better results, especially for short times to maturity. Right? And the reason for that is that the longer out into the future we go, right, so those are those later M's, the M5, M6, and so on. The further out we go, the more the diffusion component, the more the uncertainty about what's going to actually happen, what the central bank is actually going to do, dominates everything. Right? These jumps at known times, they're really most important when we're getting close to that known time. And so once we had that, then actually Jacob Skov, he visited me in Sydney, and the three of us, we did a paper together to try to do this again, using instead of using the type of estimation that I've presented to you just now, we actually went and did a Kalman filter, which is a bit more sophisticated approach than what I had there. But we got effectively the same results, right? So in that paper, we also used the model with jumps at known dates, not quite the same model, but still qualitatively the same, and we got qualitatively similar results. So that sort of confirms what I've been saying, that in this new world of these new benchmarks, we need to move to models that have these stochastic discontinuities, these jumps at known time. Here, this is just to illustrate a bit. This just shows you when we did the three-factor model, what these three factors look like. And there are two things to see here. One is that the first factor is largely flat. And that, again, aligns with a well-known stylized fact, if you will, from empirical analysis of interest rates, that the first factor driving interest rates is the factor that largely determines the parallel shift in term structure, meaning that moves interest rates for all maturities up and down. Right? And then the next factor is then the second one sort of is a twist factor that changes the slope of the term structure of interest rates, and the third one, the curvature. And this sort of shows that works in our case as well. Now, the other thing to note here is that the factor 2 actually, well, the factor 1, right, except for that very first point, which doesn't, which is really just an artifact, but it's largely positive, and the second one then flips in sign, which means that if the central bank raises interest rates at the next meeting, then that's, at least on balance, increases the chances that it will lower them on the meeting after that. This one I don't have that much to say about. It's just that the factors, okay, some are more diffusive than others, but I'll skip over that. This one is, of course, then the cube-Q plot for our factors. And that's the motivation for then further modifying this model, because what we're seeing here is that we've got fat tails in this distribution, which means that the model actually should have stochastic volatility rather than the deterministic volatility leading to the Gaussian model. And that's what we then did. We modified the model further to just make the volatility component stochastic. So this sigma there no longer is just, skip ahead a bit. So this sigma here is no longer a deterministic function of time, but rather it is represented as those two components where that V itself follows a stochastic process. Right? So this is a very common way of specifying stochastic volatility in finance. And it's actually well known from a model for stock prices known as the Heston model. And that's why we then decided to call our model the Heston-Howe-White model, because it is the Howe-White interest rate model extended with this Heston-type stochastic volatility. Now, given, again, in the interest of time, I'm not going to go through all the mathematics. It's in the paper that you can download if you're interested, and just basically skip to the results, the interesting stuff. So we can use that model and calibrate it not just to the futures contracts, but also to option contracts on the futures. And so recall that an option is a contract that I can enter into today. If I buy an option from you, then at some future date, I have the right, but not the obligation to do a trade with you. And you have the obligation to do that trade with me if you've sold me the option. If I sold the option to you, then I have the obligation and you have the right. Right? So those things exist also for these futures contracts. And of course, these options are very much dependent on volatility in their pricing. So if we calibrate a model, not just to futures, but also to options, then it's very important that we have a model that can capture better these volatility features that I've just been talking about. So what you see here is the model prices versus the market prices. So the black are the bid and offer prices for options on these futures. And you can see actually two things you see here. One is that there's a gap between bid and offer. So bid is the price at which the bank is willing to buy, and offer is the price at which they're willing to sell. And because they want to make money, those two prices are not the same. Right, so we get those two plots. The other thing is you see that they do bounce around a bit, but that's just due to the fact that they're not, these are daily prices and they're not necessarily all observed at the same time. And then we have in red the model prices, and you can see that they already at least reasonably have the same shape. But the thing is, this is based on constant model parameters. So if you've done a little bit of work in this area, you recognize, okay, for a model with constant parameters, this is already a pretty good fit. And if we then make them time dependent, then we can get much, much closer. We can't get it perfect, but we can get much, much closer to the market. Now, another feature of this model then, when we're talking about options, is the behavior of how the option is priced during the accrual period of the underlying future. Now, for the 1 month futures, the options on 1 month futures, the option actually matures when the future matures. So at the end of the accrual period, but the rate is being accrued already during that month. And for existing models, you get very strange effects for the pricing of those options because the models cannot capture the fact that your rate, that you already know much of the rate for that month once you're halfway through the month, right? You already know the first half of the month in terms of the rates, so you know half of your payoff basically. Yashchenko and Mercurio, they took some existing models, the LIBOR market model, and then they tweaked it a bit, and they came up with the red line. They said, okay, well, because we learn about what the payoff is going to be during that month that the option matures, we see the volatility basically that determines the price of the option should just decline. And they said, okay, we'll just arbitrarily say it's got to have that flat curve. But of course, that's not true, because volatility depends on whether there's a meeting date of the central bank or not. So what our model does is that if we have a meeting date during the accrual period, then the volatility drops as we get closer to the meeting date, and then it's zero, because then we know what the rate's going to be for the rest of the period. So the black curve, for economic reasons, seems a lot more reasonable than the red curve. But this is a prediction, because the market for these 1 month options is not yet liquid enough to actually be able to, for us to be able to say which who is right. But here's a criterion that we can use, right? So this is something that the model predicts. So if as the market for instruments based on these new benchmarks is evolving, we say you should see the black, not the red. If you see the black, then it says, well, then we've made a prediction that's actually come true, which is always good when you're modeling, right? But we'll see what happens. The final point that we noticed here is actually that, especially our stochastic volatility version of the model, it actually has mean reversion in 2 places. One, through this sort of standard, if it was a Gaussian process, Ornstein-Uhlenbeck process like dynamics, right? That's how you bring in mean reversion. But on the other hand, we're already getting mean reversion just to the factors linked to the meeting dates. And one can actually choose those volatility parameters based on the central bank meeting dates in such a way that we don't need any other mean reversion parameter anymore. And from an economic point, that is very nice, because it would basically say that, well, mean reversion comes from the fact that eventually the central bank has to bring the rates back to some reasonable level, right? So if they've raised the rates to fight inflation, once inflation is gone, they've got to bring it back down. If they've lowered the rates because there's a recession, eventually when the recession is over, they've got to bring the rate back up, otherwise they'll get inflation. Right? So that can be captured in the model already through these coefficients gamma, and we don't need Ornstein-Uhlenbeck type dynamics. And I think I'll close with that, just to give some chance for questions. But I'll close just with this slide, which gives you the 2 papers where you can read up on all the details that I've had to gloss over.
Thank you very much, Erik, for the great talk. Are there questions in the room first or online? Any? One question.
Which criteria does the central bank use to determine the next rate?
Well, the rate is the main lever that the central bank has to, on the one hand, fight inflation, right? So if the target rate determines the rate at which commercial banks can borrow from the central bank. So if the central bank raises that rate, makes it more expensive to obtain money, that reduces the amount of money in the economy as a whole. Therefore, bringing down inflation, right? Because inflation is just a surplus of money and a lack of goods to buy with that money. While on the other hand, if we're in a recession, part of the problem is that there's very little investment, right? So you want to make investment cheaper, and the way to make investment cheaper is to lower the rate, right? To make it easier to borrow and invest. So it's a very, very coarse instrument to try to guide the economy but it's the best one that the central bank has.
I was trying to get to the point that the central bank presumably also introduces some sort of random component in this decision. Or is it an absolutely logical thing according to some decent principles?
If you talk to a central banker, they would say it's absolutely logical based on these decent principles.
But what do you think?
Well, you know, people, they're human, right? So it's decided by a committee, and the outcome is subject to many things, right? It's a group dynamic, and who thinks it's right and who actually wins the argument. So yes, there may very well be a random component to it. But on the other hand, for the modeling, right, very often the central bank at least tries to signal to the market what they're going to do before they do it. Right? So from a modeling point of view, if that happens, it doesn't really matter, right, whether that originally was decided in a more random way, as long as it's signaled to the market what they're going to do. Then we're definitely with the stochastic discontinuity. That is being signaled to the market. And even if it's completely random, what's random is the size of the movement, because they very rarely change the rate at a date that is not known in advance. There have been, like during COVID, in some jurisdictions, there were these emergency meetings where they did do that, but it doesn't happen very often.
Thank you very much for the questions. Any other question in the room before we check online? Are there questions? Okay. Okay. Erik, I have a couple of questions for you. The first one is with your object function that you have given in one of the slides with HM that you choose to be 0.005.
Ah, yeah, I remember the one. I'll try to get back to it.
Optimal HM that you choose, or you just give it?
No, that's the tick size.
Okay.
It's based on the tick size, right? So anything below that is below the numerical accuracy of the market.
Oh, okay. Okay, so another question is that, do you look ahead of time when are the meeting dates? Or you look in the past when you do your calibrations?
Well, there's a calendar.
Okay.
So for the calibration, we need the dates in the future, right? Because we're calibrating to futures. So we need to know the dates of the upcoming. And there's an actual calendar where you can look that up.
Okay.
Yes. There are sometimes emergency meetings, right? But it has to be really an emergency. So the last one was when COVID really hit and the financial markets crashed. So they had emergency meetings to try to turn that around. And before that, I think you'd have to go back to 2007, 2008, financial crisis for emergency meetings.
Okay. Another question. So looking at when you calibrate your option on SOFR, these options are generally American stylized options. Do you convert them first to European stylized options before you calibrate, or you just do an approximation?
Yeah, we just approximate, right? We pretend they're European.
Is that
well, they're relatively short-term options, right? So I would suspect that if you actually went to the trouble to find out what the early exercise premium is, you'd find that there's not much. But no, we haven't done that. And nobody's really asked for that so far. But yeah, I mean, fair enough. Strictly speaking, you'd have to check, and we haven't.
Okay. Any good questions?
Your volatility, you steer it with the indicator functions and the Wiener process. Is there a reason why you don't do it with the increment of a Poisson process that gets 0 and 1 and in front there's something else?
I'm not sure how to interpret that question, because I mean, the Poisson process doesn't give you a diffusion are you saying that you want to approximate sort of a diffusion type dynamic of with a Poisson process, so very, very frequent jumps? Is that the direction you're going, or are you thinking infrequent jumps? Yeah, so infrequent jumps wouldn't work here for the diffusion part, right? Because you just have jumps at random times, right? So you would get neither of the two things that we feel we need, right? So if I go back here a bit to my graph, that one, right? So we've got the short rate, and that's supposed to jump at known times. The Poisson process doesn't work for that. Yes, but it's piecewise deterministic, but it needs to then jump by a random amount on those dates. But on the other hand, we have the colored graphs here, which are much more diffusion-like, right? So those are the forward rates. So if you don't have a diffusion component in there in the background, you're not going to get that. So that's why we need to drive things by Wiener process.
Thank you. Any quick questions from the online? No, if no, again, let's thank the speakers, Erik, for a wonderful talk and also for time to come to Stellenbosch.
Pleasure. Thank you very much.
Thank you, the audience online. Thank you for coming to attend. And can you please have time to chat, have a discussion outside. Thank you.